All right, so the recording is started. First thing first, so I'm just gonna let you guys know that there is a robo tutor available for this class. It is the TTP ASM tutor. I am going to share a link or not or delete it, either one or the other, right? So I am going to, I think, let me see, huh? No. So I'm going to put this into the announcement, and obviously people who do not pay attention to what I'm saying now or arrive a little bit late will kind of miss this part unless they listen to the lecture. So I'll just let them do it. Chat, GPT, tutor, put the link here and publish. There we go. Okay. So it is actually quite useful. Okay, it already has some pre kind of these are questions that I put in there to start a conversation. Basically, you can ask it for a lot of things that are specific to this class, to the way that we use the stack and the TTP ASM. So you can ask it about can you describe the caller callee agreement? Okay. So typically, if you ask this kind of question in general ChatGPT, it won't know what to answer because the correct answer depends on many things. Okay, so even within computer architecture and compiler and assembly language programming, it depends on which computer architecture, it depends on which compiler we are talking about, and so on and so forth. But this particular GPT or custom GPT is programmed using the material for this class. So it would actually tell you, what it is used, how the stack is used. It grows downward. Register D is used as the stack pointer, blah, 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 and so on. Yes. I suppose we can give it a try. Like, can you generate a study guide for an exam that will be on calling functions. Okay, and I mean this is awfully vague. We'll see what it does. Yeah, so it can do it. I cannot say whether it is correct or not. Okay, but so far it looks good. Pushing is to decrement D first and then store to D and so on. I specifically ask it not to produce actual assembly code as much as possible. So, it is not going to give you the actual homework code. Yes. The processor architecture itself is not programmed into this particular chat custom GPT. So that part is kind of uh, beyond us now. In other words, the final exam will not ask you about the pathway between the components, but you still need to know the effect of an instruction, and that one should be in the custom GPT. Huh? You can you can ask it something like this, can you help me differentiate between LDI and LD? I think that it can answer. And obviously, we are boiling some water here. Oh, oh, nice. Okay. Immediate value for LDI and then address in register B for LD. So they're all correct. So far, so good. So you can use this as a resource in order to learn and practice your concepts. But I specifically programmed this not to give you the answer to programming assignments. So it will give you some idea of how to do it, but it won't do it for you. Yep. I know most of you do not want the GPT to do it for you, but it won't even accidentally do it for you. But it is a resource, okay? It is a resource because if you want to understand a specific concept, you can ask it, okay? All right, so this is a resource. It's already in the announcement, um, and all your conversation with this particular custom GPT, I cannot see it either. So don't worry about people who attempt to actually get the answer to one of the homework assignments and they'll go like, "Oh, tech is going to know about this." Nope, I do not. Hmm? I don't think so, because the knowledge that is already uploaded to it is already incorporated in an internal format. So I cannot even get back to the source document that I used to train it or to kind of give it the context. So I don't think you can easily clone it. But instead of cloning it, you can also just upload all the modules that I have already included in Canvas because that's what I did. And I gave you very specific instructions of what to do when people ask questions. So you can do, quote unquote, the same, except you remember that your final exam will not have access to ChatGPT. So that means, you can probably program ChatGPT to do all your homework from here on all the way to the end of the semester. But without access to ChatGPT in the final exam, you kind of have to keep that in mind. Yes, you mean access to it, or you're putting the entire LLM on the calculator? Okay, well then I can tweak the tutor to specifically give wrong answers on certain dates. Yes. I haven't really tried the final exam on ChatGPT, so I don't even know whether it can do those questions or not. So, alrighty. So what we'll do today, okay, if you have read the announcements, I already have a plan for today, which is just gonna get into this sample program that I have here, okay, which doesn't do anything particularly useful. So let's go ahead and get started with that sample program. And that's a script for me to uh, update a program on a little MCU board, which is irrelevant to this class. So we'll kind of ignore that for now. Okay, cool. All right, so the program is called localvar.c. It is already in the announcement. So if you got a chance to at least take a look at it, that would be kind of cool. If not, it'll be fine too. All right. So in typical, TAC fashion, we have the C code on the left-hand side, and on the right-hand side, we're going to write the assembly code implementation of the same code on the left-hand side. The focus here is um, to kind of review things that we have talked about already. How do we call? How do we return? Okay, that's the most basic stuff about calling and returning from a function. How do we pass parameters? Okay, how do we pass arguments to the parameters of a function? We talked about that also already. And then how do we use the return value of a of a function? We have also talked about that. So the only new concept that we're going to talk about today are the local variables. There's only one in this. Well, there are two because main has one local variable, and the function called max2 also has a local variable. I understand this is not the most efficient way to implement, the maximum function to find the maximum of two numbers, but this one does use a local variable, so I'm gonna use it. It also has two parameters, which also means I can also illustrate which parameter is where on the stack. So all of those are kind of useful things. You can also feed this particular C program into the custom GPT that I just mentioned and see what it has to say about the implementation of this program. I believe it will talk about the concepts, it will talk about the stack, it will talk about the frame, it will talk about how to access the parameters and the local variable, but it won't give you the actual code of doing that. So, you're more than welcome to give it a try. Okay. So there you go. So before we move on, are there any questions about this particular program or the use of ChatGPT in the context of this class? Yes. Yes, everything is being recorded right now. Yep. All right, so let's go ahead. So the entry code is going to be the same as the entry code of almost every program that we have written so far. We just have to initialize the stack pointer, then we call main. Okay, so calling main means I have to get the return address into a register, decrement D, stda, that's pushing the return address. Then we do a JMPI to the function that we're calling, which is main in this case. And when main is all done, when we return, we just have to do a halt because that concludes the execution of everything that we want to do. So that's pretty typical stuff that we do with the entry code. So now we can go ahead and implement max2. So the entry point is max2. So now the question is, what does the stack look like? What does the frame look like when we are in the code, like line 5 of the C code of max2? So now we want to take a look at what is going to be on the stack. What is at the highest location of the frame with respect to max2? So I want you guys to answer the question. You already you should understand enough to answer that question already. What is at the highest address of the frame of max2 at the entry point of the function? The second parameter, that is correct. So that would be y, right? And then what is right below that? X, and then what is right below that? The return address. That is correct. Okay. So if those are your answers to the question that I asked earlier, then you are doing pretty good in the class, because you're absorbing all the material, okay, and we understand the stack. But what about the local variable? At this point of the execution, at the very entry point of max2, where is the local variable? It's a trick question. Is not on the stack, okay? Because the caller does not know how many bytes to reserve on the stack for local variables. So the reservation of local variables is not the job of the caller, it is the job of the callee. Is that okay? Because there are different implementations of max2. Some implementations do not need to have local variables. So that's why the caller can never tell whether there need to be local variables, and if so, how many. So that means at this point, that's what the stack looks like. And the stack pointer, okay, is pointing to the last thing that was pushed on the stack. So that means it is pointing to the return address, which was the very last item that we pushed on the stack. So that means if we need to allocate for on the stack for the local variable, the callee, which is max2, needs to do that. Okay. So we are going to go, we will use this kind of instruction. We'll put a certain number into register B. Okay. So I'll just put underscores here. And then we're going to subtract that much from the stack pointer. In other words, register B it just needs to be used. But what I really want to do is to calculate the underscore, 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 so that we can actually decrease the stack pointer by that much. So most of you look at this and will understand how many bytes do I need to allocate for local variables? A single byte, right? So that means the underscore, underscore, underscore can just be a 1, which also means I can just do a decrement D to allocate for the storage for my local variables. But I'm not going to do it that way, okay? So instead, I'll do it a very long way, okay? So the very long way of doing this is to say, okay, let's just say that we are done allocating for the local variable. So what is going to be on the stack? We got Y, we got X, we got the return address, and we got our local variable t over here. And because it is the last item that is allocated, that means the stack pointer points to local variable t. Does that make sense? Okay. So that means now I can actually calculate the offset to every single item on the stack. So this is going to be at d plus 1, and this is going to be at d plus 2, and this is going to be at, oops, d plus 3. Okay. Now, this is only for illustration purposes. Okay. So what we'll do instead to define the labels is a little bit different compared to this. So the way I'm going to define the labels is going to use max2 as a prefix because the assembler does not understand the concept of scope. In other words, if I just use y, x, and t, and if there's another function that use the same name, there's no way to differentiate between the local variables and the parameters of different functions. So using a prefix of the function is kind of important. So I look at t and go like, okay, it is at an offset of 0 from where the stack pointer points to. Okay. In other words, this 0 here is matching this 0 here because t is at exactly where the stack pointer points to. So there's no offset whatsoever from where the stack pointer points to access local variable t. The next item you would think is the return address, but no, it is max2 LVS, which stands for local variable size, which is the total number of bytes that I need for all my local variables. So you can say like, oh, okay, that's just going to be 1. Well, yes, we can say it that way, but the way I'm going to do it is also a little bit awkward. I just do it like this. In other words, I use the offset to the very last local variable that I have defined. There's only one, so it is the last one too, plus the size of the last local variable. So everything is relative. This gives me the ability to add additional local variables, especially ones before local variable t, without changing the rest of the code, because I can make very minor adjustments, and because the labels are all relative to each other, it allows me to adjust the offset relatively easily. Is that okay? All right. And then we can use this. We can use local variable size, which is LVS, and then we can do the offset to x. So that would be max 2 underscore LVS 1 plus. So this one here is accounting for the byte that is being used by the return address. Okay, so this one on line 23 refers to the size of the return address because we have to skip that one location. And then we have the rest, which is y, max2 underscore y, is defined to be max2 underscore x1 plus. So that particular one on line 24 refers to the size of x. Now, since your x is an unsigned 8-bit integer, it only takes up 1 byte, and therefore we just add 1 to the offset of x in order to get to the offset to y. So do we all understand the purposes of these labels? They are not the actual address of where to find t, x, or y. They are offsets from where the stack pointer points to get to those items. Yes. Um, so the way I write the code is I always do this just so that I have, so one, I don't have to always keep track of, who's at 0, who's at 1, who's at 2, who's at 3. And also, this way, I have symbolic names that match the variable names in the C code. So I always do this, but I do not stop people from punishing themselves. So if you do not want to define labels and use symbolic names and want to use a much more convoluted way to do this, you can always go for the scenic route. Yes, go ahead. Hmm. So the stack is occupying the highest memory portion of the processor. Nope, nope, because 255 is actually the return address from main back to the entry code. Assuming that's the only thing we do in main, yes, that is correct. Yep. Yeah. So it's better not to associate absolute addresses to where we can find various items until you run the code. So when we are constructing, when we are writing the code, everything should be relative to where the stack pointer points to. But when you run the code, then you should know exactly where each item is in terms of their absolute location. Yep. Okay. So when we're gonna run this code, I'm gonna have to tell you guys where I'm supposed to find what, and then we'll double check. We'll compare what I think the items are to the trace because we can actually see in the trace where the things are actually located. Yes. hmm No, labels are not a runtime concept. It is an assemble time concept, which means by the time this code is loaded into the processor, there's no such concept as the labels. In other words, you can define as many labels as you want to help to make the program easier to understand. None of that is actually represented in runtime, which means they do not use up any memory locations and they do not use up any time either. The values is really computed by the assembler, and all this is really saying is to tell the assembler every time it sees the symbol max2 underscore t, it is just a zero. Every time it sees max2 underscore y, it is really just three. So it is no more than I know you guys are not using macros much these days in C++ programming, but these are basically equivalent to macro definitions, which means that they're only used by the compiler slash assembler. But outside of that, once the code is generated, the labels just completely disappears. There was another hand. Yep. hmm They're not allocating anything. These are nothing more than just symbolic names with a numerical definition. That's all they are. So they're not doing anything to the stack pointer. They're not doing anything on the stack. They do not use up any memory location. They do absolutely nothing until they are referenced by actual instructions. So they are basically just symbolic names of the equivalent integers. This is completely just symbolic definitions. Yep, and they're only useful during the assemble time. During runtime, it's useless. Yep. hmm All right. So now we can go like this and go like. But wait, Tack, you are making a mistake here because this is what the stack pointer points to at the entry point of max. This is where we wanted to point to after this instruction here. So let me ask you guys, what label should I put here? Of the four labels that I have defined, which one should I use on line 13 where the cursor is? Nope. Nope. You have two more choices. Nope. Okay, you guys have managed to miss the only correct answer, max2 underscore LVS. That's the whole purpose of that label is for me to know how many bytes I need to allocate. All right. So yes, go ahead. Say again. Okay, so what does LVS stand for? Thank you. So you might want to write it down because I will not answer that question again. And I'm not even going to ask, am I mean or am I just being tagged? The answer to that question is I'm both. I'm okay with that too. No, but I'm really trying to make sure that you guys write down the notes. So when I said something about what LVS stands for, you might want to write it down because it is not obvious and yet it is important. Okay, so LVS stands for local variable size. So the way I write code is non-linear, like most of the other things that I do. So instead of just writing the code linearly until we get to the end, I write the end right away. So the end is going to look like this: load register B with max2 underscore LVS. But this time I'm adding it to the stack pointer because I'm deallocating um, the storage on the stack that was used for my local variables. Whatever you allocate, it needs to be deallocated somewhere. Okay. So I would do this right away because if I don't do it, I would forget. Okay. So I do it right away. And then we have the usual return code, which is a LDBD, increment D, and then JMPB. So I would do the return code right away because otherwise I forget. Okay. So in the final exam, okay, you will be asked to find all the flaws of an assembly implementation of some kind of C program. I would suggest you to use the same approach. Okay, look at the beginning. What are you supposed to see at the beginning? And then try to match the end to see what you are expected to see at the end. So do it in a structural way instead of a sequential way. But that's just my suggestion. Okay, it works for me. Okay, it does not mean that it's going to work for you. So you're going to have to find out what is the best way for you to spot problems in your code. And you will have plenty of opportunities to practice that. Well, okay, 3 weeks or so, but I think that's plenty of time. All right, so now we can go back. Okay, and at this point in time, okay, it doesn't matter because the label definitions can go anywhere. Unlike C or C++, which needs to have the names of the functions defined before you use them, in assembly code, you can define the labels at any point. It will still resolve them correctly. So now I can say that in between this code here, this is where I can start to implement the actual code of max2, which starts on line 5. I need to store the value of parameter x to local variable t. All right. So are we good so far about how we set up the stack, how we set up the frame, and how we take down the frame as well? So when we take down the frame, we take down or we deallocate the local variable, and then later on we also deallocate the return address. But we are not deallocating the arguments or the parameters because the actual number of parameters is not quote unquote known to the callee. And that has to do with a really kind of nifty feature of C++ where you can define a function to take a variable number of parameters. Did you guys know that? Yes? No? Maybe? Okay. So I'm just telling you that now. Okay. You can actually define a C function to take a variable number of parameters using the dot 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 notation. And that is the only reason why we push arguments in a call with the order that we specify. Because the callee really does not know how many parameters there are on the stack. Is that okay? All right. All right. So now we can say, okay, how do we copy the value of x to t as a local variable? So the template that I use typically is to load a particular register. Register A can be used at this point. I just have to be careful when we get to the return statement. But right now we are not even close to the return statement. So I load A with the offset to get to X, which is max2 underscore X here. And then I add the stack pointer to A. And now we have the address of X in register A. But do I want to copy the address of x to t, or do I want the value of x copied to t? Which way? The value. So what do I need to do at this point? The address of x is in register A at this point. How do I get to the value of x? Yep. So that's how we do it. Okay, so we dereference it. So at this point, I would say, I will give you this program. Okay, this program will be given to you at the end of the lecture, so you don't have to be too frantically copying everything down here. The concept is what you need to understand. Okay, because once you understand the concept, once you have the code, then you can kind of backfill this program with all the comments that you are going to write. Okay, because you're going to write in a way that you understand instead of me writing everything in a way that I would represent, like, oh, this register now has blah 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 in it. Are we good, doing okay so far? Okay, so this is going to be a repeating pattern. Okay, so I need to copy this to local variable t. So it's going to be a very similar kind of strategy. I load the offset of t into another register, register b. I add B, the stack pointer to B. So now B has the actual address of local variable T. So now all I need to do is to do something like this, because register A at this point already has the value of parameter X. Register B has the address of local variable T. All we need is to do a store, and we are now done. We are now done with line 5 of the C code. So I'm going to pause here and see if there are any questions regarding line 26 to line 31. Yep. Okay. So each one is doing a particular job, right? So what does LDIA max2 underscore X do? What ends up to be in register A in this case? Go ahead. So let's focus on just line 26, right? So let's focus on just line 26. What ends up in register A after line 26 executes in the assembly code? It'll be the label, right? Yeah, whatever the label is defined to be. So what is the label defined to be in this case? What is X? Max 2X is defined to be. So this is 0, this is 1, and this is 2. So max 2 underscore X is really just 2. Okay, it's just defined in a very awkward way because I want everything to be relative to the item right before that, right? So max 2 underscore X is really just the integer 2. Okay, so that means on line 26, okay, if I want to get the simplest explanation of what is in register A, it will simply be 2. But that doesn't really tell you anything about what is 2 representing in this case. 2 is representing the number of bytes from where the stack pointer points to where I can find parameter X on the stack. That is what that 2 is representing. Is that okay? But is that to the address of parameter X? It is the offset, right? So if it's an offset, it is an offset from where? From where the stack pointer points to. Yes. Okay. So that means if I need to get to the actual address of parameter X, what do I need to do? Add the stack pointer to register A in this case. That is correct. So once you have the offset, you just have to add the stack pointer to the offset in order to locate something that is on the stack or in the frame in this particular case. Is that okay? So that's a super important concept because everything that we do is on the stack. Okay, we will introduce global variables at a very late point. Okay, because there are certain things that are just a whole lot more convenient to be actually global. But right now we do everything on the stack. Is that okay? So the next so line 28 is really just saying, oh, okay, register A has the address of X. So since we need the value, so we basically load indirect, to register A so that we can go from the address to the content at the address. So LDAA, something like that is fairly typical that we do in this class in assembly code. All right, cool. Yes, it is related in the sense that um, so C++ has a different way of looking at local variables compared to regular C or just plain C. With plain C, you have to define all the local variables within the scope at the very beginning. Allows you to sprinkle those definitions like everywhere, which is nice in a way, but also messy in some other ways. The compiler does that. The compiler would actually look at all the scopes and find out at the deepest level, how many bytes are actually needed. There's something else in an x86 processor that really helps with this. It's called a frame pointer, which we do not have in TTP. So the way we get to the actual address of a particular item is a little bit different on the x86 architecture, just because it has a register called the frame pointer that can be very helpful in this case. It's always pointing to the base of the frame. But how the frame is allocated in C++ is up to the compiler to decide. I would imagine that it would calculate the maximum number of bytes that are actually needed and allocate everything at the same time. Not the whole program, just that function, because every function has a different LVS. So, correct. Yep, yep, exactly. All right. So now we can, so the next three lines, or line 28 to line 31, are basically essentially the same thing. So you can now see that the access to parameters and the access to local variables are pretty much the same. Okay. The only difference between a local variable versus a parameter, there are two differences. The first difference is parameters are pushed by the caller. Local variables are reserved or allocated by the callee. That's the first difference. The second difference is parameters always start with known values, because that's the whole idea of the caller specifying the parameters so that the callee can get to the parameters with known values. The local variables do not start with any known values at all, because all we do here is we just allocate the space. We did not initialize the location that is corresponding to local variable t. So this is also why in C++ programs, if you do not have an initialized local variable declaration, the local variable starts with some unknown value. Does it have a value? Yes. Do we know what it is? No. Okay, so that's a major difference between C++ programming versus most other programming languages, especially scripting languages. Because with scripting languages, local variables that you have not used yet usually start with a specific value. I think in JavaScript, it is undefined. When I use the word undefined, I do not mean actually literally undefined. I mean it is a very special value called undefined. So it is actually defined to be quote unquote undefined. But you can check it, okay? You can actually check whether a variable has the value of undefined in JavaScript. In C++, you cannot do that. So you have to be super careful not to use variables before they are initialized. Which programming language again? I didn't quite catch it the first time. JavaScript? Okay, I see it. Yeah, JavaScript is technically ECMAScript, because JavaScript refers to the limited application as the uh, browser client side, programming. But you're correct about the language itself. Yep. All right, cool. So we are done with line 5. Now we are moving on to line 6. Okay, we still have the value of t stored in register A, so I can kind of focus on just getting the value of local variable, no, parameter y. So it's going to be about the same thing. Okay, so now I can reuse register A, so I could do the same thing like that, and then do a LDAA. So at this point, register A has the value of y, variable, I mean, register B has the value of t, so I can now do the compare. So I would do a CMP, um, t is in register B, the register, bad, bad, bad. This is bad programming here. Okay, so I need to use B because register A actually has the value of T, so I can reuse register B instead because register B has the address of T, which I do not need to use at this point. Okay, so I want to compare T, the value of T, which is still in register A at this point, and compare that to the value of parameter Y, which is in register B at this point. So CMP AB. So the question is, what do I need to branch away? Okay, so this is a interesting question because to branch away, I actually need to do something entirely just opposite to what I can do. Okay, because I do not have a way to tell whether something is not less than something. Okay, there's only JCI and JLI. And by the way, which one should I use in this case? JCI, very good. Okay, so you guys are remembering that which one is used for signed and which one is used for unsigned comparison. So JCI, I can only use JCI. There's no J and CI. Okay, with most other architectures, there's a conditional branch for the flag being 0, but in TTP, because it is a extra risk processor, it only has one way but not the other way. So I can now say, okay, JCI to max 2 then 0. Okay, so the label is telling you that this is inside max2, and then 0 is telling you that it is corresponding to the then branch of the first conditional statement of the function. Now, if you look at the C implementation, there's only one conditional statement, but I still want to be systematic. So I always put a 0 here, just in case there are additional conditional statements, so I can differentiate between the first versus the second conditional statement using the digit after the then. Is that okay? All right. So that's just me being systematic. Okay. In other words, I'm trying to think like a compiler. All right. Okay, there's Okay, so this JMPI is basically saying if we did not take the JCI, which basically means if A, register A is not less than register B in an unsigned way, where am I supposed to go? So you have to look at the C code and ask, what if T is not less than Y in the conditional statement, which is from line 6 to line 8? What should we do? It should skip to the end of the conditional statement. So that means I'm going to skip to max2 underscore end if 0. So once again, the 0 as a suffix is telling me this is about the first conditional statement. So now I can define the labels. Max2 underscore then 0 is here. And I would even comment here and say this is the then branch of the first conditional statement, because if I don't do that, I will forget too. So this is end if 0, which is marking the end label of the conditional statement. So this way I know, okay, if I'm here, I should be implementing line 7. All right, so we look at line 7 of the C code. Okay, so it looks like we can duplicate the pattern that we saw on line 5. Okay, essentially, 6 instructions can do this, but I can shortcut this a little bit because the value of y is already in register B, right? So I can now shortcut this a little bit and just say, okay, I just have to recompute the address of local variable t, and then I'll be done with it. I can also do something even a little bit more optimized because I can go back here and go like, okay, let's not use register B here. We'll just go ahead and use register C because we do have register A, B, and C available. So that means register C will still continue to have the address of T at this point. So that means when I get here to store the value of Y, which is already in register B, to local variable t, all I need is to stc, in this case b, and I'll be done. So this is optimized, okay, based on what I know is already in register B and register C respectively in this case. So that is something that you also need to do for the final exam is you at all times you need to keep track of which register has what in it. All right. So the way you comment that is going to be, does it have the address? Does it have the value of a parameter or a variable? So you always want to comment your code so that you can keep track of all that stuff. So just this once, okay, I will write some comment so I can show you how I would describe it. So I would say that B is based on the previous code. It has the value of Y. And then register C, on the other hand, has the address of T in it. And that's why, okay, so that's why right there. Okay, so this is how I would label how I would describe that register B has the value of Y, register C has the address of local variable T. But how you would document your own program is up to you. Yes, go ahead. Mm, No, the allocation actually happened earlier. It is when we subtract B, which is the number of bytes used by local variable size, when we subtract LVS from the stack pointer, that's when we allocate it. This is already past the allocation so that we can actually use local variable T. So the allocation is done on line 13 and line 14. By the time we get to line 26, it's already allocated. This is retrieving the parameter and then storing it to the local variable. Yep. All right. So now we are done with the conditional statement, and all we have to do is to return the value of t. So the value of t is not necessarily in a particular register. We know that register C is still pointing to it, so we need a LDAC because in both cases, okay, whether the conditional branch happens or not, register C continues to have the address of local variable t. So by the time I get to line 45, register C still has the address of local variable t, but the return statement is not returning the address of t, it is returning the value of t. So that means I still need a load instruction here to go from the address of local variable t to the value of local variable t. Is that okay? All right. So that concludes the function max2. So I'm gonna kind of take a little pause here to see if there are any questions related to max2. So we are good. All right. So now we can move on to main, which is its own function. So at this point, main is not a special function anymore. It is a function just like everybody else. So that means I need to do the local variable definitions and all that stuff. So main underscore v is 0 because it is the one and only local variable. So it is at the offset of 0 from where the stack pointer points to post allocation. And then LVS is going to be main V 1 plus because it is the last local variable allocated plus 1, which is the size of the last local variable. But since we only have one local variable, it is also going to be the last local variable. And then we have main has no parameters, so that's all we need. And then I'm going to do the same thing, which is LDI B with main LVS, subtract that much from the stack pointer to allocate, and then I'll do the opposite to deallocate at the same time. So all the code should go in between, should be on line 26, I mean line 60, sorry. So line 60 is going to be the actual content of main. And then I'll do the usual, which is LDBD, increment D, JMPB, which is the actual return code to go back to the entry point. So now I can, I can stuff, whatever is in between with the actual code of main. So is everybody understanding the template of how I write functions? Allocate local variables, deallocate local variables, and return. Okay. And then once I figure out all of that, then I stuff whatever the function needs to do in between the allocation and the deallocation of the local variables. Is that okay? All right. Yes. Which lines again? Line 47 and 48. What about that? It's moving the stack pointer back up again, which means we are deallocating. And in this case, we're deallocating just the local variables because at this point, I cannot deallocate the return address because I have not retrieved it yet. So the only thing I can actually that I can deallocate would be just the local variables. But after I deallocate all the local variables, the stack pointer will be back to pointing at the return address, and that's why on line 50, that line is going to retrieve the return address. Yes. Yep. So you have to wait until you're done with all the local variables before you deallocate. All right, so now in between we have line 15, to implement over here. All right, so we have a call to max2 inside a call to max2. So how would we do this? Yes, that is correct. So we're going to do the inner max2 as if there's no outer max2 at all. And then we'll use the return value of the inner max2, push it on the stack. Then we push 55 and then call max2 again. Okay, so that is the correct order. So that means when you implement the C code in assembly code, the first thing you need to do is to think about the order of things. Okay, which part of the expression or which part of the statement needs to be done first, and then what else needs to be done, and so on and so forth. I have a text term to refer to this kind of reasoning. Is I simply call that dependency reasoning. Okay, you just look at the whole thing and ask, the outer call of max2, what does it depend on? It depends on the constant of 55. Okay, that's easy. Okay, but it also depends on the result of the inner call to max2. So that means you have to do the inner call of max2 first, right? So that's how I describe as quote unquote dependency reasoning. You look at what depends on what else. And usually, unless you have a circular dependency, which means typically there's a bigger problem involved. But unless you have a circular dependency, you can use this line of reasoning to figure out, oh, we need to do this first, and then we do this, and then we do this, and so on. Okay. So that's what we'll do here is to handle the inner call first. So the inner call is just pushing 90 as a number, decrement D, ST, DA. Okay, that pushes 90 on the stack, and then we have to do the same thing with 25, push 25 on the stack, and then we push the return address on the stack, which is LDIA dot 6 plus decrement D stda. And now that we have all three things pushed on the stack, we can now continue execution at max2, which is our function. When it returns, we have to deallocate the two arguments, 25 and 90, on the stack. So we need increment D and increment D. And now the register A still has the return value from max2, the inner max2. So we use the same caller-callee agreement that we have to push that on the stack. So that means we decrement D again, and then stda. So that would push the return value of the inner max2 call on the stack. And then we push 55 on the stack, like so. Decrement D stda. And now we call max2 again. Okay, this is the outer max2. So jmpi to max2, increment d, because now we have the two arguments for the outer call to max2 to deallocate. So line 79 to line 80 are for deallocating the arguments of the outer max2 call. At this point, register A has the entire right-hand side of the assignment. So now we just have to calculate where do we find V as a local variable. So we cannot use register A, by the way, at this point, because yep, exactly. Because register A at this point is meaningful because it is the return value of the outer max2 call, which is what I want to store to local variable v in this case. So I load this with main underscore v, which is the label representing the offset from where the stack pointer points to local variable v. Add bd to calculate the address of v, and then do a stba, and that concludes line 15 of the C code. Line 16 is not really useful because we don't have anything to interpret the exit code of main. But since I want to be consistent and just do everything to be consistent with the caller-callee agreement, I just put a 0 into register A as the return value, and now we are done. Okay. All right. So I have just done something that I strongly advocate people do not do, which is to write the entire program and then cross all the fingers to hope that it works. Actually, my hope is it does not work. My hope is I messed up somewhere at a location that I do not even know. It compiles, it assembles, because the assembly error are easy to fix. Okay, the assembler will actually tell you, oh, we have a problem here. Because I want to show you guys how to debug a program when you just make a mistake. Okay, and we're gonna all make mistakes when we write code like this because it's very tedious. Okay, and that's why people do not write code in assembly to begin with. This is also the reason why C as a programming language was invented. So the two original authors who wrote Unix basically was they were writing the entire operating system in assembly language. Yeah, not quite as tedious as this, but it is still tedious. Probably on now, this is just my estimate, okay? Probably on day 3, they go like, no, we cannot do it like this. This is way too tedious. So they invented a programming language that was not C yet. I think it's called B or before BC BCPL, before C programming language, okay, which you can look up the name of that, precursor to what we know as the C programming language. So that programming language evolved into C, and then from C we have a Shrewsbury who turned it into C++. So that, so hopefully this helps to connect things that we learn in this class to things that you learn in 360, and hopefully things that you will start to learn in 400 for those of you who have not taken 400 yet. So there's a rich history of all of these things. And then for people who think, oh, Unix, that's a 1970 something operating system, it is irrelevant in today's world. Well, I have news for those people. Your Mac OS, your iOS from Apple, they are truly descendants of Unix. Yep, BSD stands for Berkeley Standard Distribution, which is a distribution of Unix, of the original AT&T Unix. So there's a straight line connecting what I just talked about, Unix, to the operating system running on your Apple Watch, your iPhone, and also on your Mac. This is interesting. I'm sidetracking a little bit. I hope you guys were around already when Steve Jobs passed away. Did you guys remember that day? A lot of people were very sad. Okay, vaguely, right? Okay, and 2 days prior, okay, I think either a week or 2 days prior, one of the authors of Unix also passed away, and hardly anyone noticed it or remember who he was. And then when Steve Jobs passed away, everybody go like, "Oh man, Steve Jobs, you know, one of the huge figures in computer, industry just passed away." But guess what? Without the co-author of Unix, that would not have been Mac OS, iOS, or Apple Watch. None of that would be would exist. So it's I just found it to be interesting how most people, consumers particularly, do not pay attention to historical things, that are actually significant. And even computer science people, most people just go like, "Oh, Steve Jobs, passed away," and nobody actually remembered the co-author of Unix, which is also the co-author of C, also passed away. Without C, there would not have been C++ either, nor Java, nor JavaScript, nor anything that is based on C. So that would have changed the history of computer science quite dramatically. Yep. Yeah, but something that's better is questionable. It is possible. An alternate timeline. Yep. That would be, yeah, you can argue the same way with Alan Turing. What if he did not exist, right? You would, well, okay, in that case, the German would have won. Or actually, there's a very easy way to interpret that scenario. There's a TV show called, it played out a future where the United States was split between the Japanese and the German. Man of the High Tower, or yeah, Castle, that's it. Yep. So there you go. All right. So now, how do we test this program? So people would just go like, just run the whole thing and see whether we store what 90 in register in local variable v. We could do that, but we could also go through a much more detailed analysis of how the stack is going to be utilized. Okay, and I will even be kind and attach it to the end of this program. Location FF. Okay, what is it used for? Okay, is that okay? So next, what do we do? Next, we call max with 90, right? So depending on what time we are talking about, it would be 90. Actually, it would be 90 and 90 because the second call would also put 90 over there. And then FD, now this one depends. On the first call to max 2, no, I take it back. I missed something. What did I miss? Location, this is not location FE. What did we use location FE for? Sorry? The local variable. Very good. Okay, so I messed up. I messed up. Okay, so this is actually local variable v of main. Then we get to the second argument of calling max2. Okay, but we are reusing this location. Okay, the first call is going to push 90 here. The second call is also going to push 90 here. And that's 90 in decimal. And because when we look at the trace, everything is in hexadecimal. So what is the hexadecimal representation of 90 in decimal? So this is basically asking you, can you do division by 16 really quickly? So what is 90 divided by 16? What is the quotient and what is the remainder? It's too late of the time. It's too late of the day to do mental calculation. Come on, it's only two digit base 10 calculation. You guys can do it. Where's the mod button on my calculator? There's no mod button on my calculator. The percent thing does not work on my calculator. Come on. Is 5 with a remainder of 10. Okay. So that means it is a 5A in hexadecimal. Okay. You guys should be able to do this. Okay. I was reading an article about how millennials are different from Gen X. Now you guys are not even millennials. You guys are Gen Z or post Z, right? Huh? You are even beyond that. You're so they are talking about how handwriting is a lost art even within the millennials. I found it to be shocking, and mental math, not to mention, mental math is gone basically for most people, which I find to be shocking. Shocking. Well, there's always a calculator in my head. uh, okay, I just did all the calculations while you guys are talking. 25 is 16 plus 9, so it's 1 9 in hexadecimal. 55 is 3 times 16, which is 48, with a remainder of 7, so it's 37 in hexadecimal. All right. So if you have not tried mental math, for a long time, you should probably give it a try, just in case you forget to bring your calculator in the final exam, which you can do on the paper too, but some people don't even know how to do on paper. Yeah, we are talking about arithmetics. Okay, we are talking about division, how to find the quotient and how to find the remainder on a piece of paper. So it's not even mental math. Some people in my CISP 300 class do not know how to do that. Okay, which part of the government? Are you talking about the Doge or the non-Doge part of the government? Uh, because they can all do this, right? They can always go to, yeah, they can go here and go like, what is the hexadecimal? Oh, okay. Most people do not even spell out hexadecimal. They would say, what is the hex of 90? I think ChatGPT understands from the context. It shows you the calculation too. Yep. Not that I'm saying ChatGPT is not useful, but people who rely on ChatGPT to do everything, it depends, okay? Because it depends on whether what they do is going to impact their own ability to reason. Okay, there are different ways to use ChatGPT. Certain ways help you learn, and other ways would actually kind of be counterproductive. So I think you guys have to be very mindful of that. Anyway, so the third location is going to be the return address. Okay, so FB is going to be the return address, which I don't know exactly what it is. And then we have local variable at location FA. So location FA is going to be the local variable. So this is local variable T in both cases, in both invocations. So in the first invocation, this location would update to 5A because that's it will first update to the first operand, which is, let's see, 25 is the 1 9. And then it will update to 5A in the first call. In the second call, it is going to start with the 55, which is the 37, and then it will update to 5A again. So that is going to be how the stack is going to be utilized. So I work all this out first so that I can check the trace of this code against what I think should happen. Okay, so this is important when you get to do your actual homework assignment, which is not today, but the next time on Thursday, we will start to have actual programming assignment that is not done within the lab period. Okay, and it is important for you to understand how the stack is going to be used and what location is going to have what content. Oh, by the way, there's one more thing that I need to update, which is local variable v will then eventually update to 5a because that's the answer that we are storing to local variable v. All right. So getting back to debugging your program. So this is an important step to debug your program because you have to know what the program is supposed to do and the side effects on memory locations, registers, and so on and so forth before you can even compare what you expect the program to do to what it actually does. Okay, because that's the whole process of debugging. How else do you debug a program? Okay, I'm telling you something that I observed in 1990. I was a TA at UC Davis. I was a grad student, so I was a TA at UC Davis for a class that is, I would say, equivalent to our kind of like a mixture of 360 and 400, because at that time C++ was not really quite that popular yet. Okay, so the people were still programming in C. um, I would go to the computer lab in the evening because that's my shift and try to help people to get their homework assignment done. So people would tell me my program is not doing the correct thing. And then before I can even open my mouth, before I can process all that and try to locate a bug, they start making random changes to the program. They would change a less than to less than or equal to, comparing to zero to compare one. So they would do all of those tiny little tweaking to hope that one of those tweaks is going to fix the problem. What is more likely to happen? It make it worse, like much worse. Hmm? Say again. Sometimes it works. There's an opportunity that it works. Yes, the infinite monkey approach argument always is valid. The question is, are you that monkey? There's a chance that you are that monkey. Yep, but there are infinitely many chances that you are not. Okay, so this is the prediction of what the program is supposed to do. And make sure that I save the code first. Okay, and then I go to my trusty uh, refer spider. Okay, is it that boring? I took assembly language programming as a once a week class from 7 p.m. to 10 p.m. It was a great class. It was taught by, I was at San Francisco State University, but the class was taught by someone who taught at UC Berkeley. So it was taught as if he was at Berkeley. The class started off with 60 people, ended up with about 12 in the final exam. And that was during a time when if you get graduate with a bachelor's degree and preferably a master degree in computer science, companies will be knocking on your door and say, "Work with us. We are better than the other company." Yeah, those days were long gone. Long gone. Sorry? Yes, it has changed. All right. So now we take a look at this code here. Okay, this is the actual trace. Okay, and this is why I want you guys to have River Spider all set up because it will tell you what is being written to the location. Location FF has 09, and 09 is the address of the hold instruction. Okay, so it is really the address, the return address from main. So now we look for the next right over here. So we go like, hey, what happened to FE? FE was allocated, but it was never initialized. It's local variable V of main, which never got a value until we return from the second call of max2. So that's why we do not see any updates until much later. So now what is 5A? Okay, you guys I hope you still remember what the 5A is. It's the 90, right? The second argument of max2, and this is the first call. And then we go to the next right location. The 19 is the 25, okay? And then this is the return address to, it's the return address from max2, the first call of max2 to main. Now, how can I confirm that? You go to the assemble tab. You go to the assemble tab, and then you go to the corresponding line, which is the first call of max2 in main. So the first call to max2 in main is right here. And then when we return, we're supposed to return to location 37. The trace indicates that we have the right return address. Okay. So when we get into max2 the first time, the next right location or the next location to be overwritten is location FA. Does anyone remember what location FA corresponds to in the C code? Local variable T of max2. Okay. Now we can double check that. Okay, we can double check because sometimes I do not necessarily remember everything. So right there, okay, we thought that it would get an initial value of 19, and it does. And then it is supposed to update that to 5A because we found that y is greater than x, greater than t, so we overrode it. And then we go back to the caller. So when we go back to the caller, we overrode location 5D with 5A again because this 5A is the return value of the first call to max2. How do we know that in the trace? Okay, you cannot see it here, but if you scroll back a little bit earlier, register A got a value of 5A. That's because it is the return value from the first call to max2. Is that okay? And then we push it on the stack because the return value of the first call or the nested call to max2 is the second argument in the outer call. And then the 37 is corresponding to 55, which is the first argument of the outer call to max2. And then we have the return address pushed. Ooh, did I forget to push the return address the second time in the call? Nope, I did not forget. Nope, nope. Okay, so I think I might have messed up because I'm supposed to see the return address in location FB, and this is not it. Okay, so I found a deviation. I have a bug. So I don't even have to go to the end and go like, hey, we did not actually store 90 into local variable V of main. I know now that the program is wrong because I do not see the pushing of the return address from the second call. So now we go back to this code and try to confirm that. So this is, mm, yep, this is pushing the first, this is the first argument of the outer call of max2. I forgot to push the return address. So do you see how I spotted the error? And I guarantee you none of this is scripted because I cannot give you a scripted lecture even if I wanted to. My brain just does not work that way. Okay, so this is not scripted. I now need a LDIA with .6 plus decrement D STDA. That pushes the return address on the stack in the second call, which I forgot the first time. So is that helpful? Okay, so as promised, I will upload this program, to the announcement, both the C and the assembly code. the lecture is still being recorded, so you have the entire lecture, as a reference point. So once again, the idea is for you guys to document and comment the program. Okay. Um, you probably want to save the trace too to analyze and look at the trace and look at the program from the trace perspective so that you can see the transition of the call, the transition of the return, okay, and actually what value got stored on the stack at which location. Because all of that is important. That's how I would imagine someone to be studying for this class. It's not really to read a lot of material and to memorize anything, but to go through this code and try to understand exactly what each instruction is doing, and also make that connection back to the C code, because that is the most important part, is how do we connect the C code to the assembly code at this point. All right, so I will do the upload later, but right now I need to give you guys the access code to today's lab, which is related to exactly what I just talked about in the entire lecture. So that's kind of how I usually structure my classes. And I think today is particularly efficient because I got my espresso before class. I call that my turbo juice. Framed. Yes. I got framed. Hmm? Oh, yes. Alrighty.